Okay, so it's really informal. It's work that's not done. I mean, it's partly done, but it's stuff I've been working on for a long time, and it's very hard, at least for me. And the main reason that I'm interested in talking about it is to maybe get other people interested in this. So this was a program that Willy Fischler and I started very shortly after the beginning of the century. And the 18th. What we were trying to do was to understand how to go beyond string theory as we knew it already. We knew how to do string theory in asymptotically flat space-time. We knew how to do string theory in asymptotically anti-de Sitter space-time. There are some small deformations of that we know how to do. And the way that all works is that it all looks like, each different asymptotic space-time you talk about corresponds to a different Hamiltonian, or in the asymptotically flat case, you really don't have a Hamiltonian in the canonical sense. You have a scattering matrix. And except in the light cone frame, in some cases where some of us believe that matrix theory provides a definition of the theory, there's not a Hamiltonian, and certainly it's different. And it's different for different asymptotically flat spacetimes with different compactifications.
Why do you say there's not a Hamiltonian for asymptotically flat spacetimes?
Well, not a useful one. There's the usual Hamiltonian of scattering theory, which is just counting the energies of asymptotic particles. But there's not a Hamiltonian that allows you to write down a set of dynamical equations that you solve and calculate things from. Okay? For string theory, we have the answer for the S matrix.
Okay.
Okay. We're talking about string theory. I'm a string theorist. I really am, despite. So what we were looking for was something that would apply to cosmological spacetimes, be a little bit more local than normal string theory is. And we knew that's a problematic idea, because even in general relativity, there are formal arguments that local stuff is not gauge invariant. But we were willing to put that to the side and think about it a little more. And we basically thought we had a big clue. And the big clue that we thought we had was the thing that goes by the name of the holographic principle. And everybody I know has a different meaning for that phrase. And in particular, there are a whole bunch of people who think that it has something to do with quantum field theory on the anti-de Sitter space. And that, I think, is just simply a much too restricted definition of what we mean by the holographic principle. And the definition that Willy and I wanted to follow were these ideas that started with his work with Lenny Susskind and then was really developed by Raphael Busso into a statement that related areas in space-time geometries to entropy. And in particular, this is not the most general way to state what I was talking about, but if I take an object in a Lorentzian spacetime, which is called a causal diamond, you take a point, you look at the interior of its forward light cone, you find some point in that interior, you look at the interior of the backward light cone from that future point, you look at the intersection of those two things, you get a causal diamond, and it's got an interior, it's got a boundary, the boundary is null, and there's a result that says that if I look at the boundary of this causal diamond and I foliate it by space-like d-minus 2-dimensional slices, and I look at different foliated slices, there will be one of maximal area, and that's the one, so in Minkowski space, it's just the one that goes out as far as you can look. in space-times where the geometry has been expanding, that kind of gets pushed further to the future where the scale factor is bigger and so on. And Busso argued that that surface had the property that the so-called covariant entropy bound would be valid. The covariant entropy bound, just one second, is a statement, loose sort of statement, that says that the entropy associated with that diamond is bounded by 1/4 of the area of that surface in Planck units, and also that this bound can be saturated. Yeah.
Where does the classical spacetime come from? I mean, this is supposed to be...
This is motivation. This is not there. Okay? This is motivation for a certain set of relations that I will think of as eventually defining an emergent classical spacetime. Okay? So, so this was supposed to bound the entropy, and Bob Wald and his collaborators showed that by making some phenomenological assertions about the relation between entropy density and the thing that appears in Einstein's equations, energy density, and the usual kinds of energy conditions, you could, quote, prove this bound. But of course that's not a real proof, because what is this bound on entropy versus energy density? What does that mean? It just says that some plausible thing that we've never seen violated by any system we've looked at would give me stuff that obeys this bound. So Willie and I realize that you're not really going to have a proof of the covariant entropy bound until you have a theory of quantum gravity. Entropy in quantum mechanics is the entropy of a density matrix. So you have to have a definition of what the system is, what the states are, what the density matrices are. You have to specify which density matrix on your space you're talking about, what the space of states is, and so on. And then we said, well, what could it be? And there was only one sensible thing that we could think of, and this is not a proof of anything, but the only sensible thing that we could think of, remember, typically spacetimes don't have killing vectors. There's no Hamiltonian, there's no thermal density matrix. So there's one thing that you've always got in every Hilbert space, a uniquely specified density matrix, which is the maximally uncertain one. It's 1 over n times the unit matrix, where n is the number of states. And if you've got a Hilbert space which is finite dimensional, any basis you look at, that's the same thing. And if you've got a theory where you haven't yet identified what important operators are, what else could you be talking about but the maximally uncertain density matrix? So we made a strong form of the holographic conjecture, which is that the definition of quantum gravity...
You're already restricting yourself to finite dimensional matrices?
Yes, because a lot of causal diamonds have finite areas. Okay? And so our conjecture is that the correct way to talk about a causal diamond that has finite area is that one assigns a finite dimensional Hilbert space to it, where the Hilbert space dimension is related to the area by the Bekenstein-Hawking, Busso, whoever's name you want to put on it, formula, and that's the fundamental postulate of, one of the fundamental postulates of the quantum theory of gravity. And so there's this correspondence where the left-hand side is kind of fuzzily defined, it's space-time, whatever that means. And the right-hand side is very specific. It's a Hilbert space. That has a definite meaning in quantum mechanics. And then we actually knew this at the moment, a finite dimensional Hilbert space. At the moment, we knew something else, which was that a formalism involving causal diamonds had been used extensively in the past in a rather sterile way in the quantum theory of fields to define a generic kinematic framework for quantum field theory called algebraic quantum field theory, in which the essential point of quantum field theory, or the essential kinematic structure, is you've got a background space-time, and for each causal diamond in that background space-time, a quantum field theory assigns to you an algebra of field operators, which are gotten by taking the usual physicist's field operators and integrating them against functions f, which have compact support inside the causal diamond. There's zero outside. And so we said, okay, so what quantum gravity is doing that's different is two things. Number one, it's saying the causal diamond algebra, these algebras in field theory are always infinite dimensional, von Neumann, complicated stuff, and that has to do with the fact that in any small region in quantum field theory you have an infinite number of degrees of freedom. And so the essential new thing, we believe, in quantum gravity is, no, that's not true. If you've got a causal diamond with finite area, that corresponds to a quantum mechanical system with a finite number of states. And so the algebra, we don't have to do fancy mathematics. There's only one algebra. It's the algebra of n by n matrices, where n is the dimension of the Hilbert space. And we know exactly what all the, quote, observables are in that causal diamond if we make this conjecture. And then we said, if we think about the quantum field theory stuff, there's a natural additional structure we want to put on things. We want to think about the possibility that we can have two different causal diamonds which intersect. Now, if I look at the region of intersection of two causal diamonds, it's not itself a causal diamond. The boundary is null, but it generally doesn't come to a point on both ends. But there is, inside of it, a maximal area causal diamond. So you start out with a very tiny region, and you grow it, and you grow it, and you grow it, and you look and try to fit in the biggest area you can, and the areas are all finite if these guys are finite. And so you'll get to some maximal area. And we said that we will encode into the theory in the following way. What is the notion of Einstein locality in quantum field theory correspond to? What it corresponds to is that if I look at this subregion of this big causal diamond, there are some operators that commute with everything that's associated with that subregion, because there are regions in the big causal diamond that are space-like with respect to the little intersection. And so there should be a tensor factorization. And again, because we're working generically with finite dimensional stuff, tensor factorization doesn't have all of this fancy von Neumann mathematics associated with it. It's just very straightforward. Tensor factorization means the Hilbert space dimension is not prime, and it breaks up into a product, tensor product of two finite dimensional vector spaces. And that this statement translates into quantum mechanics is in the statement that H1 is O12 tensor N1, and H2 is the same O12 tensor N2, where this corresponds to those things that are measurable in the intersection causal diamond. Okay, the states that are accessible in that intersection, and these are all the states that are only measurable by observers that are space-like separated to that causal diamond. So that's the natural translation of locality into this framework, the tensor factorization of Hilbert spaces. And then we realized that we've now got a framework for encoding everything that you say about a classical spacetime into purely quantum mechanical concepts. Namely, there's a theorem in general relativity that if you tell me the conformal factor and the causal structure of a Lorentzian spacetime, you've completely specified the metric. And by giving you a sufficiently rich set of causal diamonds and specifying the areas of the holographic screens on their boundary, and all of what their intersections are, and the sizes of those, and which things intersect with which, so that I know who's causal with respect to whom. If I make a sufficiently rich set of such diamonds, I've defined both the causal structure and the conformal factor of the space-time. And so we've now translated all of that data into things that we can say purely quantum mechanically.
Okay. So you've shown that the say the space of nesting or overlapping diamonds directly translates into a conformal factor plus causal structure?
Yeah, I mean, just think about it. If you make it sufficiently rich, sure, because any area you want to measure, you can sort of fit a little causal diamond into it, and you.
Now, since geometrically the area can get to be arbitrarily small in these overlaps.
Right. So
you're going to get below 1.
Right. So no. So the correct way to say that is that the area concept breaks down when the dimension of the Hilbert space is too small, and the correct quantum mechanical concept is this: and the Hilbert space dimension just never gets smaller than 2 or 1.
They're boundary problems.
Sorry?
They're boundary problems. The algebra of observables isn't, there are observables that overlap.
That's true.
So if I look at the Hilbert space, the one causal diamond, this is up to boundary, up to observables. You can't keep written in this tensor product. Put another way, in quantum field theory, if you have
I agree with you that in quantum field theory there are boundary issues, and those all have to do with infinities.
Okay.
And
we're just going to do this.
We're just going to separate that out.
It makes sense. That then becomes an open question, not one that is obvious. You started with something that is obvious.
I don't know. No, I don't. Okay. Nothing here is intended as a derivation of anything. This is intended as a way of thinking about.
Now the quantum mechanics stuff.
Right.
What survives?
Okay. So what I can tell you is, if you take a large smooth space-time, and you take a sufficiently large set of causal diamonds, and you specify all of this data for them, that's enough to completely fix the causal structure and the conformal factor. And of course, as you make the space-time, vary on shorter and shorter distance scales, I'm going to have to work harder and harder to do that. Okay? And so my thought about that is, sure, but you shouldn't be using the space-time concept on shorter and shorter distance scales.
Okay, but these Hilbert spaces now are of dimension 10, 20, 1, 2, 3, 4, 5.
Right.
And then you presumably can follow this thing, break them up into dimension 1 Hilbert spaces, time dimension 1 Hilbert spaces.
No. You can break them up into dimension 2 times something smaller. Dimension 1 Hilbert space doesn't have any states in it at all. So you just don't. Yeah, right. So there's no sense to talk about it. There's no notion of tensor factorization of the Hilbert space into a lower dimensional space than itself. That it's not in the definition of standard tensor product.
Well, I'm still confused. So you take some big collection of Hilbert spaces, and they have a certain algebraic structure, and then on the other end, there's.
We're far from finished yet.
So we're down to spins.
But wait a minute. Are we going to get? Somehow we're going to get a space-time metric out of that, right?
Only in some very approximate notion, in the limit of very large volumes, very large areas.
Large numbers of Hilbert spaces? Is that the same thing? Or?
Large dimensions of Hilbert spaces, and Hilbert spaces that are very closely spaced in dimension. So if you allow me, I'll go a little bit further, and maybe this will become a little more clear.
Is the manifold encoded into this as well? The topology of the manifold?
The topology of the manifold will be fixed for us.
You'll assume that?
Absolutely.
And Euclidean and Lorentzian is also included?
Lorentzian is definitely encoded in this because of the notion of a causal diamond.
Your precise construction starts from the quantum mechanics, right?
Yes.
So you give me any prime factorization of a number.
No.
Right? So
No. I'm not finished. I'm not finished.
Okay, but can I ask one more question?
Yes.
In ordinary sense, the algebraic quantization approach, if you take one of your diamonds and you have this intersection region, you have operators associated with that. You have operators which commute with those, which are in some orthogonal thing. But there's also operators sort of to the future of your intersection within the causal diamond which won't commute.
Right.
Okay. So when you write your Hilbert space as this tensor product,
It's the tensor product. If I were thinking in quantum field theory language, I'd draw some space-like slice across and I'd be separating operators according to where they were on that space-like slice. Okay. So now there are a number of questions that have been asked, and let me try to start to answer some of them. So the first thing that we're going to put in is the topology of space. Now, I'm going to make, however, a radical statement about that, which is that the only topology of space that we can actually meaningfully talk about is the topology of the non-compact dimensions of space. The topology of the compact dimensions of space, I would say, as all string theorists know, is not an invariant concept. It's something that, depending on where you are in the known string theories in moduli space, the same topology looks like a different topology. You know, the heterotic string on T3 is the same thing as M theory on the K3 manifold, and things like that. All of these string dualities teach us that compact topology is not an invariant of the correct theory of quantum gravity if that theory contains the known string theories as part of their definition.
Also true of the non-compact dimensions, right? If you bubble up a little handle, it can disappear.
We don't have evidence for that in string theory, I don't think. But my definition of string theory might be a little bit more strict than yours.
Well, suppose you took one of your compact examples and you took a limit where it became non-compact, but some of the topology remained in the region that you...
Do you know examples that we've actually constructed that look like that are non-compact spacetimes where we have scattering states in the boundary and there's some funny topology in the middle?
Well, you can take a negative curve.
I mean,
Close trusted because it's not compact.
yeah.
And in the technical sense, the topology in the middle is also finite. We cap it.
You just say any geometric transition gives an example.
I think the simplest examples are Riemann surfaces, actually.
Okay.
But I'm trying to keep asking a stupid question, but where did string theory come in? Hilbert space.
String theory is not supposed to come in, it's supposed to come out. This is...
There are strings that
Okay, please don't make the mistake of mistaking induction for deduction, okay? I'm trying to make guesses about things based on what I know about string theory. Okay.
So the guess is only non-compact dimensions.
Right.
Tom, when we talk about local operators, we don't really know that we have that in string theory because the string that straddle many of these causal diamonds and only belong to any one of that in particular.
I didn't say that I necessarily had local operators, did I? I said...
Well, for factorization,
Yeah, you have operators for
Okay.
Yes, because you've got the smallest Hilbert spaces, and they have operators that act on just them, and they would be approximately local.
I believe that in string theory we all believe that there are some operators in the Hilbert space that commute with others. That's the only structure. That's the only structure I've put in here so far from the quantum mechanics point of view. The rest of it is words. Okay. So what I'm saying is that you can see how from the data that you put in quantum mechanics with these words, it is possible that you would be able to reconstruct a Lorentzian geometry. The data being something that I haven't yet been allowed to state. Okay? Can I please? Okay. So what we did was to specify a topology for a spatial slice. Okay, and this spatial slice, we've thought about two different types of space-time. We haven't thought about every type of space-time. The two types we've thought about are big bangs that don't recrunch, and time-symmetric space-times like asymptotically flat space, things of that type. And in those two cases, I would think of the spatial slice as being in different places. So in the asymptotically flat case, I'd think about a time-symmetric spatial slice. I pick a slice, I have a time symmetry operation that reflects around that slice. Where it is doesn't matter, but I'm going to use that as the center of my coordinate system. You already see here, as one might have anticipated from general relativity, that in order to talk about this stuff, you have to start talking about particular coordinate systems. The quantum theory, we know in general from gauge theory that in order to actually write down the Hilbert space of a quantum theory, we always do have to pick some sort of a gauge. And this is even more to the point in general relativity, where what we call the Hamiltonian operator depends on the coordinate system we choose. And so writing down what the Hamiltonian is and what the basis to describe the Hilbert space in always involves a choice of gauge, and I'm going to be doing that partially in this. So I'm picking a choice of gauge that starts from this space-like slice, and I'm going to put in the topology of that space-like slice for lack of more imagination by putting a lattice on that space-like slice. And that lattice, its geometry is completely irrelevant. Its metrical geometry doesn't matter, but it does tell me the relationship, the topological relationships between points. With every point on that lattice, okay, I'm going to specify a sequence of Hilbert spaces such that the nth Hilbert space at the point x is some particular Hilbert space to the power n, where that means tensor power n. And the way you should think about that is in terms of pictures like the following. So this is something like what you would get in a Big Bang sort of space-time. I would start out with a space-like slice, which you think of as down here. These are two nearest neighbor points on the lattice. Each of them have associated with them a sequence of Hilbert spaces that gets bigger and bigger as n gets bigger and bigger. And that's, sorry? N stands for, according to the formulas that I told you about, it stands effectively for the area of the causal diamond at type n. That is to say, the dimension of this Hilbert space is growing by a power each time I increase n, so that's increasing the area by 1 unit. And so the log of the dimension of this Hilbert space P is the unit of area that this particular space-time is using. Okay? And we'll see that that has something to do with compact dimensions.
N refers to the type of
N,
diamond that is?
No.
Is it 1, 2, 3, 4?
Area of the
Or is it 10?
This is, it starts at 1. This would be a Hilbert space of dimension dim p. And then this would be dim p squared.
And the one to the left of it is?
Okay. Now, the one to the left of it has exactly the same sequence of dimensions. This is specifying a time slicing from the Big Bang. That is to say, at each point, I come up until my causal diamond has some particular area, stop, then I go on to the next one. If you look at that, that's a discrete kind of time evolution, but it gets less and less discrete as time goes on, because what's discrete is the area, and the area typically in normal sorts of space-times grows like a power of the proper time as I go up a causal diamond, and so the discreteness in time is getting smaller and smaller, and it's roughly that the discreteness in time is 1 over the energy of the biggest black hole you could stick into a region of that size, okay? A black hole whose horizon is just a rough way of understanding how the time is scaling with the entropy. Okay? This is just a kinematical description of the Hilbert space. Now, when I say nearest neighbor point on the lattice, that's a statement about this overlap. What I do to fit the lattice topology to the space-time geometry is to say a nearest neighbor point on the lattice corresponds to an overlap that's almost maximal. That is to say, the difference at a fixed n between the Hilbert space at point x and its nearest neighbor y is just by one factor of this same fundamental Hilbert space P. Okay? And then for each further point on the lattice, I will specify some overlap, but that's actually part of the dynamics. Deciding what that overlap is going to be fixed by an incredibly complicated set of consistency conditions, which I will now try to explain to you. So, why did we do this? The reason that we did this was we wanted to talk about this completely holographic theory, but we wanted to talk about some way in which it had, in cosmology, the concept of a particle horizon in it. The way we can do that in this framework is to say the following. The Hamiltonian for this system operates in a very large Hilbert space. The large Hilbert space is whatever I get to when I take n to infinity. By the way, it might be that the proper time parameter is related to the area in such a way that the area evolution stops or asymptotes to a finite area as time goes to infinity. Example, de Sitter space. Okay, where the maximal causal diamond any observer will ever see has a finite area. So you shouldn't make the assumption that because I want to talk about time evolution forever, that I will be constantly increasing the area of my causal diamonds. Okay? And in fact, I'll show you another example in a minute where the problem goes in the reverse way. So what's happening here?
In some sense, is worse as time passes.
Sorry?
We talked before about the fact that this is kind of a discrete time evolution. You said in normal circumstances, it becomes less and less discrete as time passes. In de Sitter space, when you use a scheme like this, it becomes very discrete as time passes.
Yeah, in that sense, yeah. The next ansatz is going to be that the Hamiltonian has the property that, well, what is it? It's not really Hamiltonian, it's discrete, it's a sequence of unitary transformations, finite time evolutions, and they change with time in such a way that at the time that corresponds to the observer living in this causal diamond, the degrees of freedom that are captured in this causal diamond are decoupled from the rest of the degrees of freedom that will eventually be encountered as the Hilbert space available to this particular observer gets bigger and bigger. And so that's a constraint on the Hamiltonian, namely the unitary operator at time n, or area n, is equal to Vn times tensor Wn, where Vn is a unitary operator in the Hilbert space Hn with little n, and Wn acts in the tensor complement of that in the big Hilbert space that you eventually reach if you just let time go off to infinity, which might be finite or infinite dimensional.
So the Hilbert space for each x, is that right?
There's a different Hilbert space for each x. Right now I'm talking about a particular x.
And so the unitary transformation just acts in that x and doesn't couple to do anything to other x's, right?
Well, just, you're right, but, okay. The way it's coupled to other x's is about to come.
Okay. So now you're getting around the problem that as you n increases, as time increases, dimension of the Hilbert space grows, right?
But it doesn't. The dimension of the Hilbert space that's coupled to your original degrees of freedom grows.
The dimension of Hn of x is dimension of
that grows. But the unitary evolution operates in the whole big space that you get to at the end. It just has the property that it...
The real Hilbert space you're talking about is the n goes to infinity.
The n goes to infinity limit.
Limit of this thing, which is defined.
It's defined by the limit. Yes. At any finite time, it's defined, okay? And there's a question of what happens to the asymptotic.
All the Hilbert spaces are the same.
That's true.
So this is just an infinite dimensional Hilbert space, period.
Yeah, but it's structured in a very particular way. It has I'm not saying that that structure is intrinsic to the Hilbert space, but I'm specifying specific finite dimensional tensor factors of that infinite dimensional Hilbert space as part of the definition of the dynamics of this system. And I'm talking about operators which are such that they decouple those tensor factors from the rest of the Hilbert space up until some finite time of the time evolution.
It's certainly critical because I think actually David's comment that all those evolutions Hilbert spaces are the same is not true in this context. I think the formal n goes to infinity limit is a non-separable Hilbert space.
I think that really, no, that's clearly not true, for example, in the de Sitter case where it's a finite dimensional Hilbert space.
I'm just saying the formal limit of what you have written on the form so far is a non-separable Hilbert space. You'll have a different additional structure.
No, sure, I'm sorry. Yeah, okay. You're absolutely right. There's a certain point at which I have to decouple time evolution from n evolution. And I told you about one example of that, and let me tell you about the other example of that, which shows you why in this context, asymptotically flat space and de Sitter space are really very, very different from anti-de Sitter space. And it's something all of you know, which is that if I think about this in anti-de Sitter space, something dramatic happens to the relationship between time and area. Namely, this is the conformal boundary of anti-de Sitter space. It's a cylinder. So if I think about little causal diamonds that are much less area than the de Sitter curvature radius, they behave like normal causal diamonds in any Lorentzian spacetime. But as I make the proper time bigger and bigger and bigger, at a finite proper time, essentially the anti-de Sitter radius, the causal diamond hits the boundary. The area goes to infinity even though the proper time has remained finite, and from that point on it stays infinite. And there is a time-like evolution on the boundary, okay, which is very much decoupled from the proper time evolution in the interior. And this, I think, is the characteristic feature of anti-de Sitter space that makes it be an infinite dimensional theory, a theory of quantum fields living on the boundary. I mean, there's more to the argument that it's quantum fields, of course, than this. And the fact that it's got a time-like Hamiltonian and that thinking about time-like evolution in this theory is an interesting thing to do. In Minkowski space, of course, the conformal boundary looks like a causal diamond. And in de Sitter space, there's not a conformal boundary, but the boundary of what any observer can ever see is also a causal diamond. And time evolution and area evolution are much more closely coupled over here. So, okay. Now, what's the rest of the specification? So the specification is for each point, x and y.
Can I just ask, are you going to tell us what V and W actually are?
No. There's one example we've worked out. I'm going to tell you a very strong consistency condition on V and W. It's an infinite set of consistency conditions, which I've only found one solution of. And I talked about it here many years ago. And it's hard. And so I don't know any other examples. So to get to that, let me let me say that for two random points, x and y, not nearest neighbors on the lattice, I'm going to let the dimension of this overlap Hilbert space more or less float. What I mean by that is its specification will be part of the way that I try to satisfy the dynamical consistency conditions I'm about to tell you about. And that specification has to satisfy some obvious things, namely, as I take a walk on the lattice that takes more and more and more steps, it shouldn't be that the overlap gets bigger. It could stay the same for a while, can get smaller, but it shouldn't get bigger as I take steps away from a single point. That condition is the only one that we specify, except for the fact that for nearest neighbors, the overlap is p to the n minus 1 at the time when the total area of the total dimension of the Hilbert space is p to the n, saying that these things almost share all of their information. That's what it means to be nearest neighbor causal diamonds. What you should think of these different sequences of causal diamonds as is, if I think about in traditional geometry a time-like observer, then the time-like observer has a sequence of causal diamonds which are given by cutting his path into units of some proper time, and then you make the proper time bigger and bigger away from some space-like surface, which might be the boundary surface, or might, as in this picture here, be time-symmetric proper time intervals around some fixed time reflection symmetric space-like slice. And the sequences for fixed x, you should think of in traditional geometry as I had a space-like surface. There's a time-like trajectory that goes through that space-like surface. And at each point there's a different one, and we're looking at the causal diamonds of the observers on those different time-like trajectories. So again, I'm trying to make a quantum mechanical construction that mirrors what we might have expected from that geometrical construction. Okay. So,
your lattice you're starting with has a metric defined. You're given.
No, it's the only thing you're supposed to think about is the topology of that lattice. So, okay. So, we have a notion of nearest neighbor. That's a topological concept.
Okay, but that defines the metric. You can associate with that metric.
Okay. But that metric has nothing to do with the physical metric. So in the example that we worked out, the metric of the actual space-time that emerged from our geometry depended only on the number of steps in the walk between 2 points on the lattice. And it didn't depend on the fact that the lattice geometry had this rigid Euclidean metric on it. Okay?
Number of steps is easy. So you could have, for example, an ultrametric lattice here.
No, that would not have the same topology as flat space, an ultrametric lattice.
What do you mean by that? There are a lot of lattices.
That is absolutely correct, and only some of them have the topology of d-1 dimensional flat space. Well, you know ones that do, okay? Any regular lattice that you write down has the topology of d-dimensional flat space. If it's no, I'm not restricting myself. I can leave out all kinds of points, and I still have the topology.
I have to go to my physical. I mean, I'm ignorant. I really don't know what, if I'm given a set of points, lanes, which is my nearest neighbors, what is...
That space that you've defined is a topological space, in addition to being a metric space.
No metric.
I
Can I just interrupt? I have to go to my physical point.
Yeah.
I'm not walking out in protest or something.
A lattice should be a graph.
What?
A graph?
Right now, I want you to think about a cubic lattice or
think about the simplicial homology defined by the
Yeah, I mean,
That'll give you the topology of it.
I really, Dave is sitting here. He can tell you what the topology of a lattice is much better than I can. It's something it's definitely a well-defined concept in mathematics to talk about the topology of any metric space, in particular a lattice. And I'm saying to you, here's this lattice. The geometry of the space-time that will emerge will have the same topology as the topology of this lattice, but it'll have a metric that's determined by other considerations. And we have a worked out example of that, in which the geometry defined by the lattice doesn't have rotational symmetry, but in the limit of large causal diamonds, the geometry that we define does have rotational symmetry. And really looks like more and more as you get bigger and bigger causal diamonds, it really looks metrically like flat space. So the metric on the lattice in that example is completely irrelevant, though the topology is. Okay, and that connection comes through this steps on the lattice being related to the actual metric in space-time. Okay. Where am I next? Okay. So that's the basic setup, and then there's a consistency condition. And what's the consistency condition? Well, part of what I said is that for any 2 points, hn of x and hn of y are related by, this is on of x and y, tensor something else, and hn of y is on of x and y, the same space. So this is n of x, and this is some other space n of y, and this is the same Hilbert space. But I've now also specified for you a dynamical evolution equation in each of these sequences of Hilbert spaces that's associated with an individual point. Now I've got this Hilbert space On, which is shared between 2 points for every pair of points. I haven't yet specified for you what it is, but here's a consistency condition that it has to satisfy. When I think about evolving a state in hn of x and a state in hn of y, and then I think at this time n what state I've got, I can ask what density matrix that prescribes in the overlap. That's some density matrix, one given the point y and its evolution, and another given the point x and its evolution. Those two density matrices must be, up to a unitary transformation, exactly the same density matrix in order for the formalism to be consistent. And that has to be true for every pair of points at every possible time. It's an enormous set of dynamical consistency conditions. And in the geometry that I talked about here many years ago, the dense black hole fluid, we found one really stupid, simple solution of that, where we were sort of forced by those consistency conditions to prescribe exactly the same evolution at each point, and the overlap rules had to have a very, very simple form in order for this to be consistent. And then we showed that in that system, and I don't have time to go over that again here, that system in a coarse-grained way looked like a flat FRW universe with the equation of state P equals rho. And so there was an emergent geometry that came from the one system we were able to construct that actually satisfied all these complicated consistency relations. So the challenge to me is you want to see a more normal space-time. That space-time was completely crazy. You'd like to see, radiation-dominated FRW or something that you really could live in. And I don't know how to do that yet.
Can you do flat space?
Flat space
That's
with
Minkowski space, no dynamics. Static.
flat space.
Well, better yet, small perturbations about that.
Let's start with flat space and then we'll ask.
Okay. Well, I'll tell you how I think about flat space, and you'll tell me if I can construct a set of causal diamonds that have the right properties, okay? But I don't have a Hamiltonian for flat space because I don't think the right way to think about flat space is in terms of a Hamiltonian, but rather in terms of a scattering matrix. And what I will show you, if I have enough time, is to show you how to think about scattering states. But the main thing that's missing in everything that we've done is really dynamical equations. So this is really a talk about a proposed kinematics for quantum gravity, rather than a dynamics, with one exception for one particularly peculiar spacetime. Okay. So,
can you do some sort of crude quantum spacetimes which never get very big and which would not be right? I'm just trying to get a feeling for what these things are. I mean, you keep writing Hilbert spaces, but you've never said an operator.
I can write down little models, with low-dimensional Hilbert spaces that satisfy all these consistency conditions. If you don't force me to have an infinite lattice of them, I can do that. I don't think it's terribly interesting. I got absolutely no insight out of doing that. You do it for 4 Hilbert spaces. It doesn't look like anything. I think that's what quantum gravity should look like. That is to say, if you look microscopically at quantum gravity, it shouldn't look like anything you ever thought about before. And it's only macroscopically that it's going to look sensibly like space-time. And that's hard. That makes it difficult. I'm hiding behind my ignorance. What can I say? Okay. So, do I have, no, there's nothing else interesting here. How do I turn this off? Does it?
I mean, what bothers me in this whole game is that, you're really working in this infinite dimensional or very big dimensional Hilbert space.
I live in de Sitter space, David.
An enormous finite dimensional.
Yeah.
You're starting out your formulation at some point in a very small subspace.
Right. So that is something that, if you're comfortable with cosmology, you should be expecting. Because if I think about a Big Bang cosmology and I think about an observer back at a very early time, that observer, by principles that everybody always invokes in talking about, acausal fluctuations and acausality in setting the initial conditions for the CMB, everybody claims that that Hilbert space is separated from everything else up until the time when it comes into causal contact. So the standard structure that we say in words always invokes this idea that if I have a Big Bang Hilbert space, it's got a small causal diamond which in the early universe doesn't interact with anything else. That's what a particle horizon means. And we just built that into an actual quantum system. The small causal diamonds in an asymptotically flat spacetime just have to do with the fact that if you insist on looking at very small distances, eventually you'll come down to a point where you don't have too many degrees of freedom left. And if you really believe the holographic principle, that's precisely what you would expect. Okay.
I mean, I'm not what you mean by degrees of freedom. It's a...
What is entropy?
You have this big Hilbert space. That's the thing you're working with. You can't associate with this small causal diamond. You have a subset of that.
Right.
Which I suppose means there is a severe constraint on the nature of the states or not.
That's right.
But that doesn't mean you don't have the degrees of freedom. You're working in the framework. You're working in. And you make a little step here. You have operators that act in that full Hilbert space.
No, if you make a little step, you have operators that act in a slightly bigger Hilbert space.
Bigger and bigger.
Bigger and bigger, right. Yeah.
So can I ask, I'm sorry if you've already explained this, but if you just take an ordinary quantum system and you say you start with some sequestered set of degrees of freedom, and then you open a door to another region and now they can interact with more and more, that can happen just in ordinary quantum mechanics.
Absolutely.
So what else do you need to be talking about gravity?
Okay.
To be talking
I think most quantum systems don't have this very elaborate set of consistency conditions that I'm talking about. So that I think of as something that's rather characteristic of quantum gravity. One way to think about that, for those of you who like the Wheeler-DeWitt equation, there's the discussion in the Wheeler-DeWitt equation of many-fingered time and the fact that you can move forward in different places in different ways, and then you can come back to the same point. And there's a consistency condition, which are the commutators of the energy density operators at different space-time points, that at different space points at a fixed time, that are supposed to guarantee the consistency of all these different time evolutions. And this, I think of as a discrete analog of those consistency conditions. This is saying that when I look at a certain region of space-time, it could be seen by different observers. And different observers will, in general, have different Hamiltonian evolutions that describe what's going on as far as they're concerned. But there's this overlap region that they both see, and so there should be at least a unitary transformation that relates the density matrix on the overlap as seen by observer 1 to that seen by observer 2. That's what these consistency conditions say. So that has a very, geometry, gravity flavor to it as far as I'm concerned that I haven't seen in any other system. And I tell you, when we tried to do what Mark suggested, which was to set up little spin systems and build up from that, we were able to do it for a few, and then it got incredibly complicated as we started to try to make the system bigger and bigger, and we couldn't solve it, and we didn't get much insight by thinking about little systems. So these things, when the systems are little, they don't look much different than ordinary quantum mechanics with spins, and when they get big, somehow they're supposed to look different.
Any evidence that string theory fits into this?
Yeah, so let me get to that. So this is another now principle that we put in, which was the following. One of the things that a lot of relativists, when they see me talk about this, get very nervous about is that people in general relativity, and me, always thought that the theory of quantum gravity had to do with fluctuating space-time metrics. That there was a quantum variable called the space-time metric that fluctuated.
Well, not the causal set people.
But I didn't say every general relative. Okay? And if you look at this formalism, it ain't so. The geometry that we're building here is built up in terms of fixed quantum mechanical concepts. The dimensions of Hilbert spaces, overlaps, tensor overlaps between Hilbert spaces. Those, in a particular dynamical realization of this, there will be all kinds of consistency conditions on those, but they'll be fixed. They won't be fluctuating quantum variables. The fluctuating quantum variables are some kind of operators that live in these Hilbert spaces. So the other thing that we did that's completely independent of everything that I've said so far is to try to think about what the quantum variables should actually be. And so if you think that the fundamental thing is the holographic principle and the holographic screen, and the variables all live there, you should try to think about something that has to do with the holographic screen. And so there are a couple of things that you should say before beginning to talk about that. One is the holographic screen, if it has finite area, can't really be thought of as a manifold. It can't have a set of continuous functions on it that's an infinite dimensional set of functions. Because if it could, you would be able to have an infinite number of degrees of freedom, sort of one for each independent function in that space of functions, at least. So you should be able to take the holographic screen and pixelate it into a finite number of pixels if it's got a finite area. And then the degrees of freedom you associate with each pixel should have a finite dimensional unitary representation of their quantum algebra. So first let me talk about pixelation just a little bit. Pixelation, the usual way you think about it on your TV screen, is you have this thing that from far away looks like a continuous TV screen, but you divide it up into little areas, and each one of those is a pixel. In terms of functions, what you're doing is saying that you're replacing the basis of functions on the continuous TV screen by a finite dimensional basis which consists of functions which are 1 in one pixel and 0 every place else. So the essential thing you're doing is replacing the algebra of functions by a finite dimensional algebra. And then once you think about it that way, there's a much nicer way to do this for many spaces. Let me remind you that all holographic screens are compact, okay, or at least for finite area causal diamonds, they're compact. And so there is a famous way of making compact spaces have finite dimensional spaces of functions in them, which is called quantization. That is to say, if the space of functions that you're thinking about has some kind of a Poisson structure on it, you can think of the algebra of functions as a limit of matrix algebras with finite dimensional matrices. And that limit of matrix algebras approaches the commutative algebra of functions with a first correction, which is the Poisson bracket on the algebra of functions. And there's an elaborate mathematical theory of this by now, geometric quantization, deformation quantization, and so on. It's particularly nice for Kähler manifolds, which are fairly nice and ubiquitous in string theory. And there's one particular example of it which is so simple that you can teach it to your undergraduate quantum mechanics class. Namely, if I think about the holographic screen for asymptotically flat space in 4 dimensions, which is a 2-sphere, then the way to pixelate it is to think about the set of n by n matrices. The set of n by n matrices can be thought of as matrices in the n-dimensional representation of SU2, and therefore they transform as a sum of spherical harmonics going from 0 up to some maximum, and they form a nice closed associative algebra of matrices that approximates in the limit as n goes to infinity the space of all spherical harmonics on the sphere. And what's going on here is the 2-sphere has a natural Kähler form, it's volume form, and that volume form is being geometrically quantized. This is also called solving the problem of Landau levels on the sphere. If you look at an electron propagating in a magnetic field which is uniform on the sphere and do the quantum mechanics of that problem, you get a finite dimensional space that depends on the magnitude of the magnetic field, which is the Kähler form. And so the finiteness is determined by the radius of the sphere. And so this is sort of a very natural way of thinking about pixelating the algebra of functions on a holographic screen. Now, what else does a holographic screen have? Well, a holographic screen is a null surface. It's a space-like surface sitting on a null surface. So if I look at a pixel in the naive sense on the holographic screen, there's a null direction going out through that pixel. And there's a little transverse plane which tells me what the orientation of that pixel is in the ambient spacetime. And that looks like a nice thing to think of as the degrees of freedom associated with that pixel. So many years ago, Cartan wrote down an equation which Roger Penrose has used extensively that encodes those degrees of freedom. And it's this equation. You take a spinner, you hit it with the gamma matrix, and then you take the fermion bilinear vector current, dot that into the gamma matrix, and say that's equal to 0. That's a nice Lorentz covariant equation. And as we all know, because we've solved the momentum space Dirac equation, it implies that this vector psi bar gamma mu psi is a null direction, its square is equal to 0, and that this spinner is a transverse spinner which determines a transverse plane. This is psi in the sense that if I look at psi bar gamma mu 1, gamma mu k, the anti-symmetrized gamma matrices with k greater than or equal to 2, those all lie in a fixed transverse plane in the d-dimensional Lorentz space. So the data that correspond to thinking about a null direction, those of you who remember Misner, Thorne, and Wheeler, there's this little chapter about spinners as being a flagpole plus a flag. Okay, that's what this is in 4 dimensions. The information about a null direction and a transverse bit of space perpendicular to it is encoded in this equation. So we think these are the natural variables to talk about. And you should have one of those for each direction, for each pixel. And so what that means is that the variables should be thought of as elements of sections of the spinner bundle over the holographic screen. That spinner bundle has to be pixelated, of course, because the algebra is pixelated, but that's a well-known construction, namely in fuzzy geometry or non-commutative geometry of that type. If I have a matrix algebra, the spaces of vector bundles over that matrix algebra are all spaces of rectangular matrices. Which one corresponds to which vector bundle in the continuum is something you have to do work for. But if I look at operators of the form psi ka, let's say ia, where I equals 1 to k, and a equals 1 to k plus 1, and the conjugate psi dagger bj, which is the opposite orientation rectangular matrix. Those are the two things for the 2-sphere that converge to the spinner bundle on the 2-sphere. K by k plus 1 and k plus 1 by k matrices are the two chiral bundles on the 2-sphere. So now I think about these variables, the SAs, those are our variables at each point, and I want to quantize them in a way that has a finite dimensional Hilbert space. Well, if I'm in a space which is asymptotically flat in d dimensions, there's a unique way to do that, which is to write down these commutation relations. N represents a particular pixel, SB of M, anti-commutator equals delta AB. And I'm going to put a delta NM. You might have thought that variables associated with different pixels are independent and should commute. But this equation has a scaling symmetry for it. That's broken by this quantization rule, but the scaling psi goes to minus psi is not broken by the quantization rule. So if I think of that as a local gauge symmetry on the holographic screen, I can do a Klein transformation with that, a Z2 gauge transformation that turns relative commutators into relative anti-commutators in the standard way. And the nice thing about doing this is two things. Number one, those of you who are string theorists undoubtedly recognize that these are the commutation relations that define the representation space for a single massless supersymmetric particle in d dimensions. This is just what you get from the supersymmetry algebra if you fix the momentum of a massless particle. We were just talking about a null momentum over here. And so the natural degrees of freedom in this system, I claim, are supersymmetric particles. You can make that much more explicit in the following sense. if you really make the pixelation go away by taking very large holographic screens so that your sphere at infinity becomes very large and therefore almost continuous, then you get Lorentz invariance back. How do you get Lorentz invariance back? Well, the continuous sphere has a conformal group, and the Lorentz group is the conformal group of the sphere. If you've got the conformal group of the sphere, you can ask for the solutions of the conformal killing equation dqa equals, let's see, this is dm, covariant derivative on the sphere, equals gamma a EAM on the sphere times QA, and this is, sorry, AB QB, and this is really DM AB QB. So this is the conformal killing spinor equation on the sphere. It's conformally invariant, which means Lorentz invariant, and the space of solutions of this transform as a Dirac spinor under Lorentz transformations in space-time. If you take these commutation relations and take limits where your basis of functions or delta functions concentrated at a point, and then multiply them by these guys, so the S's converge to SA delta of omega minus omega naught on the sphere, where the SA's just satisfy this commutation relation without any M's and N's, and I take SA QA alpha, then the commutation relations of these operators are indeed the supersymmetry commutation relations with a null momentum that is 1 comma omega. It's the null momentum going out, sorry, omega naught, going out through that point of the sphere.
Tom, you could have chosen any number of different Klein transformations at that point. So are you required to choose this particular?
Well, it's a gauge transformation, so you choose the one that looks nicest. The thing that's nicest about this, as I told you this morning, is that once you do this, and you're thinking in the realm of non-commutative geometry, then it's very natural to do it again and again and again, which is to say you do it in blocks. You take your function algebra to be an algebra of block diagonal matrices, which have a natural permutation gauge symmetry associated with them, because which block you put where is not something that's fundamental, it's just something that has to do with writing them down. And if I treat that as people in matrix theory are wont to do as permutation statistics of particles, then with these minus signs, I get the connection between permuting two fermions and a minus sign that I expect from the spin statistics theorem. So this gauge symmetry is minus 1 to the f. Once you've got minus 1 to the f, you can do Klein transformations, as we know in field theory, to make some fermion fields commute with others, but we never do that because it's inconvenient. You don't know that, Sean. If you read old enough books on field theory, they'll tell you that different fermion fields can be made to commute with each other. Okay.
These are fermions at different points, really.
These are fermions at different points on the sphere, if you want, or associated with different basis elements in the space of sections. Okay. So this is, I believe, the connection to string theory, because in fact you can motivate string theory, and if I were teaching string theory again, I would definitely do it this way, by starting out with the supersymmetry algebra in 11 dimensions and just talking about BPS states and supersymmetry representations, and then you're led to string theory Not the way it appears in Joe's book, but nonetheless, I think that's a way that leads uniquely to string theory, just from symmetry considerations. And so I think this way of thinking about the theory of quantum gravity leads you to the conjecture that we happen to know appears to be true in all of the string theory examples we've got, namely that when we have infinitely large causal diamonds with asymptotically flat symmetries, we get exact supersymmetry back. And here it's forced on you by your choice of what the quantum variables are. So I think this leads not just to quantum gravity, but to supersymmetry and therefore string theory, if you think about it. Now, these commutation relations are special to d-dimensional asymptotically flat space. One of the things I did with them, with Tomeo Fiol and Alex Maurice, is we tried to say, okay, let's just do this directly in four-dimensional asymptotically flat space, and let's get a theory of the real world. And we failed. What you can show if you do this directly in four-dimensional asymptotically flat space, just with the variables that 4 dimensions prescribe for you, is you get a supersymmetric theory of massless particles. They're, of course, just the kinematics. We can construct the Fock space of a supersymmetric massless particle field theory, but it's chiral multiplets. Okay? You've got supersymmetry. The structure of this, because the sphere geometry built in the SU2 symmetry, we can talk about what the overall spin is. Usually the SUSY algebra by itself leaves over a helicity for a massless particle, and you can specify the spin of the ground state, and you can get any spin you like. But our structure had built into it the SU2 rotation algebra, and so we found that the things we got no choice were the chiral multiplet rather than the gravity multiplet. After a week or two of disappointment, we realized this is a good thing, because it tells you what you really should be doing is working with the number of SUSY generators, that you would have had in 11-dimensional space, so that you're forcing yourself to get up to helicity 2, but you just choose different commutation relations. And so this leads into what was the thing I really wanted to talk to you people about, which is the way I'm trying to think about compactification. So the way you think about that is you have these objects, psi IA, but they've got another label, M. Psi dagger N B J. These are a bunch of things that satisfy the, and this is for 1 pixel on the holographic screen of 4-dimensional flat space. Okay? These satisfy the commutation relations which you expect from rotation invariance, delta ij, delta AB. And then there's something else, ZMN. What an M and N label? Well, the philosophy that I've expounded here is that I'm trying to think about a compactification down to 4 dimensions. So I've got more spatial dimensions, but they're compact. If spatial dimensions are compact, they're invariably fuzzy in this way of thinking about things. They should be talked about in terms of non-commutative fuzzy geometry. And so what these M and N label is a basis of sections of the spinor bundle in some fuzzily compactified higher dimensional space. And that space should, if I were allowed to take that spinor bundle arbitrarily large, then I would reproduce the bundle of sections on some particular manifold. Okay? Now you can formulate in terms of this algebra the conditions that I'm still able to construct one 4-dimensional SUSY generator, but that far from classifies these algebras. Okay? So there are some conditions on the algebra that basically tell you I can go through the SUSY construction again. But you'll get different spectra depending on now the commutation relations of these z's with themselves and with the psi's. One way to think for string theorists about what these z's are like is these things, since these are sections of the spinor bundle independently, these are sections in the bundle that you get by tensoring two spinor bundles, so they're the spaces of forms. And so you can think of these things as brane charges wrapped around the compact dimensions. And what I'm trying to construct is to try to think about the geometries that we now know about in string theory should be there in 4-dimensional compactifications, and think about how they will appear as algebraic structures of this type. However, there are a couple of really interesting points that I think you get from the basic general framework. These algebras, okay, are algebras with finite dimensional unitary representations. Those representation spaces don't have moduli. They have discrete data. Okay? So as long as this geometry is kept finite, even in the limit where I take these indices off to infinity and reproduce an infinite holographic screen in the non-compact dimensions, the internal geometry will not give rise to moduli. They will just be frozen at some point, and they're not frozen at some point because there's some potential and I minimize it and so on. They're frozen at some point because of the kinematics. In order to imagine getting them unfrozen, what you have to imagine is that you can take simultaneously, when I take the non-compact holographic screen to infinity, I can also take limits in the internal geometry that give it an infinite number of degrees of freedom. Okay? Now, that's something that makes sense if there's some length scale in the theory that is much, much longer than the Planck scale. Okay? So if I look at an algebra like this, okay, roughly speaking, the relation between geometry and the number of degrees of freedom in the non-compact spaces is that K goes like Rm Planck, where Rm Planck is the radial size of your causal diamond. It's in 4 dimensions, it's just the square root of the area of the causal diamond. The way you see that is if I think about an algebra like this, and I think about the entropy of the Hilbert space in which I represent that algebra, it's e to the k times k plus 1 times the logarithm of d, where d is the representation space of the representation of this single pixel algebra for fixed values of these indices. Okay? This thing, therefore, plays the following role. This thing plays the role of the volume of the compact dimensions in higher dimensional Planck units. The entropy is given by a size, a dimensionless size in, so the real formula is K goes like Rm Planck times the square root of log D. Okay? Where M Planck is the d-dimensional Planck mass, and that's then the formula for the that's the formula that gives you the logarithm of d, the Kaluza-Klein formula that says that this is M Planck 4 squared over M Planck d squared. So log d is telling you how many degrees of freedom the eternal space has at a particular point in ordinary spacetime. Now, something really interesting about this is that if I say I know I live in de Sitter space and I know what the entropy is, that's a number. It's 10 to the 123. Okay? That number is composed in this formula of two pieces. Now, in order to really be able to describe particles in my non-compact space, I have to make the k's very large. Okay? In order to describe large volumes in the compact space, I have to make log d very large. But if this whole entropy is given by some fixed number, I can't do that arbitrarily. All right? I won't have a decent continuum non-compact four-dimensional space-time description, okay, unless the volume stays fixed and reasonably small. So if you put in the numbers, for example, with our real radius, these kinds of formulas are inconsistent with ADD type of non-compact dimensions, very large millimeter-type dimensions. The formulas are also saying to you that if you're in de Sitter space, you've automatically frozen all moduli. Okay? Because log d is some finite number. You've got a finite dimensional representation. The changes that you can make in this structure, if any, we haven't even put in dynamical consistency conditions yet. But the kinematics will not allow you to make more than discrete changes in the structure, and therefore there are no continuous parameters which would then show up as massless fields in the in four dimensions. And if I'm in de Sitter space and I have a real bound on how big this manifold can be, then that puts a bound on how massless things can ever be. Because moduli are always going to come out by taking limits in here where the dimension of this representation is infinite. So there's an enormous amount of work that has to do with, I think, sort of interesting mathematics having to do with Kähler quantization of some of the manifolds we know in string theory, thinking about how to do this for odd-dimensional manifolds where Kähler quantization doesn't work, what kind of Poisson structures would come out on a G2 manifold. I think I know some answers to that for certain G2 manifolds, those that are K3 fibrations. But there's a lot of stuff to do here having to do with filling in the very important details of how you describe compactified geometries in terms of these formulas. And that is something that has encouraged me to keep on with this despite the fact that I'm not able to answer these troubling dynamical questions that everybody asks me about. You know, how are you going to compute the S matrix? How are you going to do this? How are you going to do that? I don't know the answer to a lot of those things. Those seem to me to be much harder problems than trying to think about how to algebraically classify supersymmetric compactifications in the sense of the holographic formalism. So the formalism does lead to supersymmetry in a very natural way, and it leads to the idea of compactifications in a very natural way, and the project of figuring out the mathematics of that and how to classify those compactifications is something that is, I think, a worthwhile and achievable project, something where one could really make real progress, as opposed to the dynamical issues where I find myself rather stuck. They're very interesting, and I can tell you privately, if anybody wants, all kinds of conjectures about them, but I've been able to think more clearly about these sorts of problems than about the others. Okay, I've gone on for a really long time. After a while, I managed to shut you all up. Not on purpose, but just because you got so bored with what I was saying. And so I'm going to quit. And you can ask any questions that you like to ask about it.
In view of the time, maybe you can take the questions in private?
Absolutely.
Can I just make one comment? So this program that you outlined at the end, I mean, it strikes me that your chances of success for spheres or tori or K3s are much higher than they are for the generic kind of Calabi-Yau manifold that we would like to compactify on. And it's a little reminiscent of, if I may say, the early success in matrix theory formulations was great so long as you were only doing tori and only going down a few dimensions. But then you start to run into real problems. And I'm concerned that this may suffer the same fate.
Okay, so there are a couple of things to say about that. If you think in terms of fuzzy compactifications, many of the old problems of matrix theory actually go away. Okay. You can formulate, basically, one simple thing to do is to do the torus compactifications is you can fuzzify them and you can make them ZNs instead of circles. And when you do that, what you get is supersymmetric matrix quantum mechanics again. There's no more field theory around. You get formulas that look very much like they're going to converge to the field theory formulas when those formulas actually make sense. But what I would advocate doing is keeping all those n's in the ZNs finite and taking the limit n goes to infinity at the end. If you remember, many of the problems in matrix theory there were plausible arguments that they would actually go away when n went to infinity. For example, the really disastrous thing that happened when you compactified 6 dimensions and there were these so-called massless gravitons, and the dual theory involved gravity, and you really didn't know what you were doing. There were arguments at that time that in the n goes to infinity limit, that would go away because those gravitons are repelled from the Kaluza-Klein monopoles, which are the real physical graviton. And so if there's a way of setting up the theory so that you don't run into problems till you take the n goes to infinity limit, there's a chance of getting rid of that. As far as your other comment is concerned, the Kähler quantization looks fairly similar for K3 and Calabi-Yaus, right? You have to know about the Picard lattice, and we do know that for a lot of Calabi-Yaus, and you have to know about the dimensions of the spaces of sections of holomorphic line bundles. And we know that in a lot of cases, and people have used that in the string theory literature. So I'm not as pessimistic about doing three-dimensional Calabi-Yaus. The thing I'd really like to do, because it's the thing that seems to me the closest to phenomenology, is to figure out how to phrase F theory in this language, and that I don't yet know how to do. And the other thing that I think I have some ideas about, at least for K3 fiber G2 manifolds, is how to formulate this for G2 manifolds where there's obviously no symplectic structure, but there is possibly a Poisson structure, at least for those examples. So I think the parallel is not exactly analogous, and once you think about fuzzy geometry, I think matrix theory will look a lot better.